Welcome back to my Udemy course. Now we'll be talking about the analysis of algorithms. So there are some certain components when you are looking at an algorithm. You have to consider the time complexity and the space complexity. The time complexity is how much time an algorithm takes to run, and space complexity is how much space an algorithm takes. It is very difficult to obtain the absolute time an algorithm takes because of the different environments. And now that space complexity is not really much of a problem because RAM is really cheap. Let's look at these 5 elements, an array of 5 elements, and an array of 11 elements. An algorithm will take less time to work with fewer data elements than one with more elements, meaning that the one with 11 elements will take more time to process than the one with the 5 elements. So now let's look how to measure time. Algorithm 1 in the picture has linear growth, whereas algorithm 2 has a quadratic growth. A linear time complexity is considered better than a quadratic time complexity because as the input size increases, a linear algorithm execution time grows proportionally to the input size, whereas a quadratic algorithm grows far beyond that and it's just not really reliable. Now let's look at the types of time complexity. There's worst case, there's best case, which almost never happens, and then there's average case, which requires the understanding of numerous statistical methods, making it very complex. We typically look at the worst case because that's the one that we like to consider, and it has the highest chance of happening. Now let's look at the RAM model of computation. In this format, we have infinite memory. Each operation, so plus, minus, multiplication, division, and equal sign, it takes a unit amount of time. And every time you access memory, unit time is consumed. And data may be accessed from the RAM or the disk, but it's assumed that the data is in the RAM. And the picture on the right just shows like the breakdown of how this works in the RAM model. Now let's look at time complexity of the bubble sort, which we discussed in the last video. So looking at that image, you can see that it develops an algorithm, a formula for the algorithm, which is Pn squared plus Qn plus R. As you may know, this is a quadratic because the highest term is n squared. And this makes this really inefficient. And when we spoke about last time how this is least efficient when the elements are sorted from biggest to smallest, this is a prime example of that. And this only worsens the case for the bubble sort because a quadratic time complexity is very bad. Now let's look at the bubble sort code, which again you have access to and you can use whenever you want. Now let's look at big O notation. This is a pretty complex topic, and you can always come back to it after reviewing the later units. So what is the definition of a big O notation? A big O notation describes the upper bound of the time complexity or space complexity of an algorithm, focusing on its behavior as the input size grows towards infinity. The purpose of this is that it helps express how the runtime or memory requirements of an algorithm scale with the size of the input, providing a new abstract way to analyze the performance. So the worst case scenario, big O is typically represents this. However, it can also be used for best case and average case analysis. Asymptotic analysis is the idea that big O ignores constant factors and lower order terms, focusing only on the highest growing term for large inputs. So if we go back a couple slides, you can see that it's Pn squared plus Qn plus R. So when looking at the big O notation for that, we would just completely eliminate the Qn and the R because it's not the biggest exponent. So now let's look at the comparison of running times. So accessing an array using the index does not depend on the size of the array, which means that it's O to the 1 notation. The time to go through all the elements in an unsorted array take O to the n time. A loop inside of a loop, or a double for loop, typically represents O to the n squared time complexity, which is not one that you do not want. And that's it for this video.